Okay, just doing a test here. Looks like I've got my transcription running. So today we're going to continue on with t-tests. So we start looking at the one sample means t-test. Now there's two other t-tests we're also going to look at in this video. So that'll be all of this video of looking at the three types of t-tests that we'll be looking at in this week's lab, Lab 4, we'll be using there. All right, so at the end of the last video, we did the one sample difference of means test using the Z-score, right? So we use the Z-score as our test statistic when we have a very large sample size, right? Next, we're going to do, right, the same kind of test, one sample means difference of means test. Or we're going to be using not the Z-score, but the T-score. Why? Because we use the T-score when we have a smaller sample size, okay? So when to know when to use the Z distribution or the Z-score versus the T distribution? Well, it comes down to two main factors. One is the size of the sample and whether you know the standard deviation of the population or not. Remember, if you don't know the standard deviation of the population, we're going to approximate it using the standard deviation of the sample. So kind of the simple rules here for you knowing whether you're going to use the Z distribution or the T distribution, right? You're going to use the Z distribution when you have a relatively large sample size, right? So your N is going to be over 30, and you know the population standard deviation. But on the other hand, if you have a relatively small sample size, under 30, and you have to use the sample standard deviation to approximate the population standard deviation, you're going to go with the T distribution or the T-stat, right? Because remember, as I showed you in the last video there, when we have a large enough sample size, we can approximate a normal distribution, and therefore we can use a whole bunch of assumptions when we have a normal distribution like the Z distribution. But when we have smaller and smaller sample sizes, our frequency distribution does not follow that nice symmetrical normal distribution anymore. It starts to flatten out into a more platykurtic distribution, and therefore to correct for this, we don't use the Z distribution anymore. We have to use a T distribution as our test statistic. Okay, so when we can't use the Z stat, we have to go with the T stat, right? We can use the T stat for basically doing three types of what's known as T tests, okay? So like I said, we've already looked at the one sample means test. We'll do one more where we're calculating the T stat. And then we're going to do two other T tests. One's called the independent sample test, and one's called the dependent or paired samples test. Right? So here's the three tests. And here's the one sample difference in means test. So just a summary of what the test consists of, right? One sample. So we're basically with the one sample, we're trying to see if the sample belongs to a larger population or not, right? So we're testing the difference between the sample to the overall population. So it's continuous data. We only have one sample, and we're just seeing if that sample belongs to the larger population, right? Parametric guess. So essentially, to visualize this, you can imagine that if we have a sample closer to the overall population mean, it's more likely that that sample is coming from that larger population. But as we start to get samples that deviate further and further away from the population mean, it becomes more and more unlikely that that sample actually came from that larger overall population. So once we start to get very extreme samples, right, sample means that's very different than the population mean, it becomes more and more unlikely that that sample was actually coming from that overall population, and therefore likely came from a different population. So that's in essence what the one sample means t-test gives us. So let's do an example. So I'll use my hometown example again. So your scenario here, you're curious whether the average people per household in the village of Maringo, Saskatchewan is less than the national average. Let's get some data here. So you do a survey of 25 households in Maringo, and you get a mean value of 2.03 people per house. while the national average is known to be a little higher, 2.61 people per household. So there is a difference, but we're wanting to know whether the Marengo sample, right, is substantially statistically different than the national average. So we don't know what the national standard deviation is, but we do know the standard deviation for the sample from the Marengo sample, and that is 1.5 people per household. So again, we're going to be following our steps to conduct a classical hypothesis testing, but this time we've added one more. In the previous video, we looked at 6 steps, but now with t-test, when we're calculating the t-stat, we're going to add a 4th step kind of in the middle there, and that's doing something called calculating the degrees of freedom. So the t-stat is different, and then you have to calculate what's known as these degrees of freedom, and I'll show you how to do that in a little bit. So in this example, right, we're dealing with a very small sample size, 25, right, households in the survey, so a small sample. So we're going to be doing a t-stat and not a z-stat calculation. So the first things first, we have to formulate what are going to be our null and alternative hypotheses. Well, our null hypothesis, right, is going to be that the Marengo sample mean is greater than or equal to the overall population mean, that being the mean of Canada, the nation mean. That's our null hypothesis, our default hypothesis, and our alternative hypothesis is whether that Marengo sample is less than the national or population mean. So the second step here is determining what test are we going to use. Should it be one-tailed or two-tailed? And what kind of test stat are we going to calculate? So I've kind of given away a couple of these already, right? So let's do a couple more steps here. Let's pick our level of significance. So again, you can pick any alpha value you want, but a standard one is 0.05. So we'll set an alpha value to 0.05. And now we can delineate the regions of rejection and non-rejection, right? So in terms of the type of test we're going to be doing a one-tailed test, because the way we formulated our question is that we're wondering if the Marengo sample mean is significantly less than the national average mean. So we're going to set our rejection zone to the left there, right? One-tailed, left-tailed test. So if our test stat comes back in this zone, we're going to reject the null hypothesis. If it lands anywhere to the right of that rejection zone, we're not going to reject or fail to reject the null hypothesis. So essentially, diagram form, there's our non-rejection zone, 95% of the area underneath the curve, and then the left-tailed, one-tailed test, our rejection zone being on the left side there. So our population mean for the national for Canada is 2.61 people per household. Our sample for Marengo is 2.03. Now the real question is that sample mean going to land within the non-rejection zone or within the rejection zone? So now to determine that, now we have to calculate the test stat. So how do we determine the t-stat in this case? Well, there's our data, right? We need our sample mean, our population mean, we have our sample standard deviation, and our sample size. So there's a formula for the one sample means test that we're going to use there, right? We're taking our raw score for our sample minus the population mean. If we have the population standard deviation, we can use that, or we can approximate it using the sample standard deviation divided by the square root of the sample size minus 1. So if we plug in our values there, or our t-stat, right, plug in our sample mean of 2.03 people per household minus the national average. Here's our sample standard deviation divided by our sample size minus 1. That gives us a t-stat or t-value of minus 1.89. So that's our t-stat. Now, just to remind you, right, there's a slight difference between how you calculate the t-stat versus the z-stat, right? T-stat has that n minus 1 to account for the smaller sample size, while the z-stat just has the square root of n. So you can also go to the Excel spreadsheet, right? So there's a tab right there, number 5, t-test. So I've entered the data, the population mean, sample mean for Marengo, sample standard deviation, and our sample size. Down below, that's where I've done the calculation right there. So all those values are entered in that expression, and it gives me a value of minus 1.89. Again, that's our t-stat. Okay, so we've calculated our t-stat. Now we got to figure out whether we're going to reject or not reject the null hypothesis. Well, to do that, we're going to compare our t-stat or our t-value to a critical value, just like we did with the z-stat. But instead of using a z-table or z-score table, we're going to be using the t-table. So the critical value that we're going to compare our t-value to is going to depend on a few things. It's going to depend on our significance level, our test type, whether that be one-tailed or two-tailed. We've already said we're doing a one-tailed test, and that degrees of freedom. That is further away from the middle of our distribution than the critical value. That's going to tell us that we're going to reject the null hypothesis. So we have to figure out what this critical value is going to be. So I'll get into a little bit, what is this degrees of freedom that we have to do with the t-stat that we didn't have to do with the z-stat? Well, the degrees of freedom basically gives us an idea of how many values are able to vary within our sample. It's basically related to the size of our sample. So in a one sample means difference test, it's pretty straightforward how to calculate the degrees of freedom, or sometimes just referred to as DF. It's basically your sample size minus 1. So for our example, right, we had a sample size of 25 households. So to calculate our degrees of freedom, we just minus 1 from 25. That gives us degrees of freedom of 24. So now we know that we're dealing with a one-tailed test. We have a alpha value, a significance level of 0.05, and a degree of freedom of 24. So that's all the information we need to know to look up what the critical value is going to be in the t-table. So let's go to our t-table. So the way to read the t-table, in this one in particular, at the top here, you have your one-tail versus two-tail test. And here you have your significance levels, right? So for our test, we have an alpha level, significance level of 0.05. And then along the side, that's where our degrees of freedom are, starting at 1, all the way up, in this case, to 1,000. So we've calculated our degrees of freedom to be 24. We have a significance level of 0.05, so we basically cross-reference those two in the table, and that gives us a critical value of 1.711. Right, so there's our critical value, minus 1.711. And we just calculated the t-value of being minus 1.89. So we can see that our t-value has landed us in the rejection zone. Right? So since our t-value is more extreme or further away from the middle than our critical value, that's going to tell us to reject the null hypothesis in this case. So that brings us to making their decision, the final decision. So given that, right, our t-value is in the rejection zone, we decide to reject the null hypothesis. And basically in terms of this scenario, that means that we find that the number of people per household in Marengo is significantly less than the national average at a 95% confidence level, right? If you change the confidence level and the significance level, you likely are going to get a different result. Maybe, maybe not. So what about the p-value, right? P-value is useful to calculate, right? Because that tells us the chance or probability that we're going to commit a type 1 or false positive error. Unfortunately, calculating the p-value for a t-test is not quite as straightforward as for a z-test. That is because, as you saw with our t-table, it's not very continuous. But if we try to estimate what our probability is going to be, so remember we calculated a t-value of minus 1.89. All the values in the t-table are positive, so we just change the t-value from minus 1.89 to plus 1.89, which lands us right where that black dot is, right, between 1.71 and 2.64. So that tells us, if we look up at our probabilities, right? These are basically our probabilities up here. It lands at somewhere between 0.05 and 0.025, so a little bit lower than 0.05. So as an alternative, we can go to one of these calculators, right, to get a more precise idea of what our p-value is going to be. So I'm going to enter my t-score 1.89, my degrees of freedom 24. We're working with a 0.05 significance level, and I'm doing a one-tailed test. So that gives me a p-value of 0.035. That tells me that based on this, I have about a 3.5% chance that I'm falsely rejecting the null hypothesis, right? And I'm committing a false positive or type 1 error. Okay, so that was for a one-tailed test, but what if we slightly change the scenario or the premise of the problem, and instead of doing a one-tailed test, we did a two-tailed test. Remember, the two-tailed test doesn't care which one is bigger than the other, right? It just cares whether there is a significant difference between the two, between the sample to that of the overall population. So let's say if we reframed our question, instead, for our research question is now, is there a significant difference between the number of people per household in Marengo to that of the national average? Before we were wondering if Marengo is smaller. Now we don't care whether Marengo is larger or smaller. We're just wondering if there's a significant difference between Marengo, the sample, to the national average. So our calculated t-value is going to be the same. That's not going to change. And we're going to use the same confidence level, 95% significance level right there, alpha value 0.05, degrees of freedom, right? Our critical value for the two-tailed test is now going to be different. So the value that we're comparing our t-stat to is going to change because now we're doing a two-tailed test instead of a one-tailed test. So we're going to have the same degrees of freedom. We're going to stick with the same alpha value, 0.05. So there it is in the green there. Same degrees of freedom of 24. Now we get a critical value that's higher, 2.064 for the two-tailed test compared to 1.711 for the one-tailed test. So even though our t-stat is still the same, now we have a critical value of 2.06, not 1.71. Okay, so now that our t-value is less, than our critical value, we're now going to fail to reject the null hypothesis because our t-value is less extreme compared to our critical value. So you can see here, we rejected the null hypothesis for the one-tailed test, but for this two-tailed test, because we changed the critical value, we failed to reject the null hypothesis. So just by framing your question differently, you can get a completely different result in terms of what your final outcome is going to be. So this really highlights the importance of choosing what type of test you want to perform and between a one-tail and a two-tailed test, and also the importance of choosing the appropriate significance level. So just to summarize here, with our one-tailed test, we had a critical value of minus 1.711. Our t-stat is minus 1.89. So in that case, our t-stat landed in the rejection zone, so we rejected the null hypothesis. Our two-tailed stat, our critical values are more extreme now than our t-values, which are the same that it was for the one-tailed test. So in this case, we failed to reject the null hypothesis. So this illustrates just by choosing to do a one-tail versus a two-tail test and completely determine whether you're going to reject or fail to reject the null hypothesis. So again, we can go and calculate our p-value now for our two-tailed test, This is another calculator right here. So two-tailed right there. Now we have a p-value of 0.07 for the two-tailed test. So telling us that we have about a 7% chance that we're going to commit a type 1 error when we already set our significance level, our alpha value, to 0.05. So because our p-value is greater than our alpha value, that's another reason why we're not going to reject the null hypothesis. So this illustrates again, right, the importance of making understanding the effects that a two-tail versus a one-tail test might have on your ultimate result, right? And the difference between a one-tail and two-tail test in terms of which one you're more likely to commit a type 1 error, false positive, or a type 2 error. So those are the things to keep in mind when choosing to do a one-tailed versus a two-tailed test. Okay, so that's the one sample means difference test. Let's look at the second t-test, which is the independent samples t-test. So it's the middle one here. So in this case, we have two samples. Right before, with the one sample test, we were comparing a sample to an overall population. But now with the independent samples t-test, we're going to be comparing two samples to see if they are statistically significantly different from one another or not. So just a summary here, basically kind of the same in terms of the one sample t-test, but in this case, we're not dealing with one sample, we're dealing with two samples. We're dealing with continuous variable still, and this data is considered to be parametric. So here's a table we'll be looking at quite a bit overall the next few lectures, right, which basically shows us different main types of statistical tests that we can do based on the type of data that we have, whether it be nominal, ordinal, or continuous, and what type of test that we want to perform. So we just finished doing the one sample difference in means test, which was using continuous data, where we have one sample. Now we're dealing with two samples with continuous data. So we have a couple options here. For the parametric option, we can use the two sample difference in means test. If our data we find is not parametric, which we'll go into later how to determine when your data is parametric or not, we'll use another version called the Mann-Whitney rank sum test for non-parametric data. All right, so let's do a scenario here for independent samples. So imagine there's a stats prof that wants to compare two classes to see if they perform statistically different on the midterm exams. So class A has 25 students with a mean score of 70% and a standard deviation of that score equal to 15%. Class B had 20 students. They had an average grade of 74% and a standard deviation of 25%. So the prof wants to know at an alpha level of 0.05, right, is there a statistically significant difference between the mean grades of these two classes? Again, you can see that there, right, 70% grade for one, 74% grade for the other one. There is a difference of 4%, but is this statistically significant at the 0.05 level? So the idea with the independent samples test is that now we're dealing with two samples, right? So we have two samples here. So the closer that they are, right, the more likely they're coming from the same overall population. But as that, as those sample values start to get further and further apart, more different, right, there becomes less and less likely that they belong to the same population, and more likely that they belong to two different populations. So that's essentially what the independent sample test is doing. So again, we're going to be following our basic steps here in hypothesis testing. The first thing we're going to do is formulate our null and alternative hypothesis. So our null, right, is going to be if there's no significant difference in the mean test scores between the classes. The differences are just due to random sampling error. And our alternative hypothesis is that, yes, there is a significant difference in the mean test scores at this significance level. So in this case, we're just curious in the scenario whether there's a difference between a significant difference between the samples or groups. We don't care whether class A or class B is higher or lower than the other one. So in this case, just because we're interested in whether there's a difference or not, we're going to go with a two-tailed non-directional test. So again, we're dealing with relatively small sample sizes. So we're going to use the t-stat and not the z-stat. And because, again, we're dealing with two separate samples, we're going to be using the independent samples t-test. So let's significance level or alpha level. I just set it to the same one that we've been using so far, 0.05. So that's, we're dealing with a 95% confidence level that we're going to get the right answer using this type of test. Now we got to calculate our degrees of freedom. With the two independent samples test, the degrees of freedom calculation is a little bit different. So in this case, this formula here, degrees of freedom, is equal to n1 minus 1 plus n2 minus 2. The n1 is the sample size for the one group, the n2 is the sample size for the other group. So in our scenario, right, sample size for n1 is 25, sample size for n2 is 20. So we plug those values in, right, we get 24 and 19, we add those together, that gives us a degrees of freedom of 43. So we need that degrees of freedom, of course, in order to look up our critical value from the t-table. So we got all the information we need. We got our degrees of freedom, we have our alpha level, and we know that we're going to be doing a two-tailed test. So if we go to, right, we're going to go to our t-table here. We're doing a two-tailed test here at the 0.05 alpha level. Our degrees of freedom, now with this table, it's a little tricky because down here for our degrees of freedom of 43, you have to interpolate between 40 and 60, right? So your critical value could be anywhere from 2 to 2.021. So the t-table is not very useful in this case. So an alternative is to use one of these calculators. So I'm going to go and plug in my degrees of freedom. I'm going to keep my probability level, my alpha level at 0.05, hit calculate, and it's going to give me my t-value, right? Two-tailed plus or minus 2.02. So that's my critical value. So 2.017 approximately. So that's critical value, which makes sense because that 2.017, right, would fit in somewhere between those two values in the red square right there. So now that I got my, just another tool here, calculator, there's a link up there. It gives me the same result, which makes sense, 2.017 for 43 degrees of freedom and a significance level of 0.05. So this calculator is actually pretty good because it gives you lots of options to do different types of calculations. So we'll be using it on and off throughout the rest of this course. All right, so let's delineate our zones of rejection and non-rejection, right? Here's our critical values. It's two-tailed test. So we're going to have the minus value and the positive value for our critical values. Now we have to calculate our t-stat. Now with the independent samples t-test, calculation of the t-stat is not nearly as straightforward as with the one sample mean different test. There's a lot of in-depth calculations. So these are some of the formulas that you have to use, determining things like sum of squares, pooled variance. So all of these pretty in-depth, very drawn-out calculations. But if you actually were to do the calculation, it would give you a t-value of minus 0.67. So that's our t-stat for this calculation. So again, what you usually want to rely upon, not to have to do these large onerous calculations where it's really easy to screw up, is to use another one of these calculators here. So for this calculator here, right, I have my two groups, right? I can enter the label for each of my groups here. I put in the mean score, right? So 70 for one class, 74 for the other, standard deviations for each of those, and the sample size n for each of those. You go and hit calculate now, and it'll give you your t-stat. So again, just to show you how to use this calculator, it allows you actually to put in the data itself, but if you just want to use the mean, standard deviation, and the sample size. So I'm going to go in and label the first column class A, second column I'm going to label class B, enter my mean for class A is 70, standard deviation 15, sample size is 25. For class B, I had a mean grade of 74. standard deviation of 25, and a sample size of 20. So there I go and hit calculate now. And here I get my results. So there is my t-value right there, 0.6652. Right? So again, because we're doing a two-tailed test, we're going to take both the positive and negative version of the 0.6652. So let's just round it up to 0.67. So let's put that in our diagram here. There's our critical values. Right, there's the positive t-value, the negative t-value. So we can see that our t-values are much closer to the middle of our distribution compared to the critical values. So they land well within the zone of non-rejection for the null hypothesis. So we know that we're not going to reject the null hypothesis. So basically, we're going to be saying that the differences in the midterm grades between Class A and Class B was not significant at the significance level of 0.05, right? But let's go and calculate the p-value anyways. Again, p-value for a t-test is not straightforward as a z-test, because we have to go back and interpolate in this table. So if we wanted to do it, the way we could do it, remember our t-value is 0.67. All the values are positive in the t-table. So it's somewhere within this purple box here, which if we go up to the probabilities, corresponds to a probability of around 0.5. But again, pretty vague in terms of what the exact p-value is. So again, we can go to one of these calculators. That calculator I just showed you also gave me the p-value for the two-tailed test equal to 0.0 or 0.5095. So that means, that tells me that I have about a 50% chance that this test would give me a type 1 or false positive error. So again, another calculator that you can use where you can enter the t-score, the degrees of freedom, the significance level. Oops, let's go back there. The significance level for a two-tailed test, right, gives me a p-value of 0.509. So about 51% chance that I'd be committing a false positive type 1 error using these results. Okay, so let's do another example of an independent samples t-test, but now I'm going to show you a little trick how you can use Excel to calculate the t-value. So this is in a tab in the Lecture 7 Excel workbook that you can find in Moodle. So the tab's called test_independent samples. So now instead of the midterm grades, we're going to be looking at the final grades between Class A and Class B for this example. So here's the data, right? Just a simple data set, Class A. Here are the grades for Class A for final grades, and here are the grades in percentage for Class B in those two columns. So our research question is similar, right? We're wanting to know if there's a statistically significant difference in the means of the final grades between Class A and Class B. We're going to be using, right, those same steps in classical hypothesis testing. First thing to do is state our null and alternative hypothesis. So the same kind of idea. Null hypothesis is that the final mean grade between Class A and Class B is the same, right? Alternative is that there is a significant difference between the mean grade between Class A and Class B for their final grades. Right, so we have two samples here. So we're doing the independent samples mean test, and we're only interested in whether there's a difference between these two samples. So we're doing a two-tailed test, not a one-tailed test. So let's again set our alpha value to 0.05. We can set it to 0.1 or 0.01 if we want to, but let's again just use the 0.05. Then we're going to have to delineate the regions of rejection and non-rejection like we did in the previous example. But now I want to show you how to use the data analysis package in Excel to determine your t-value as well as your critical value. So you don't have to rely on those tables, the t-tables. So again, in Excel, you can go, if you don't have the data analysis package, so the data analysis tab is found under data. If you go to data and you do not see this data analysis tab on the far right there, you likely have to go and do an add-on. So you go to File, and there should be an add-on. Go to options, add-on, and it'll allow you to add the data analysis tool pack into your Excel spreadsheet. So once you hit the data analysis tab, it gives you a whole bunch of different stat tests that you can do. So the ones that we're interested in is the 2-sample t-test, but the problem in Excel is that there's 2 options. There's one option for the 2-sample t-test assuming equal variances, then there's another one assuming unequal variances. So which one to use, So unfortunately for this, you have to do another quick statistical test called the F-test, which tells you whether the variances between your 2 samples are different or not. So let's quickly do that. So if you click on this test right there, so here's my data in the tab. So I go up to the data tab there on the right, I go to data analysis, opens up the dialog box. So I can see that's where my t-tests are for equal and unequal variances, but I have to figure out whether they're unequal or not, first of all. So to do that, I'm going to do my F-test. So I'm going to enter my data, I'm going to drag over top of my first column, my second variable, drag over top of the data in class B. I'm going to set my labels, and I'm going to set the output, the results, starting in that cell right there. So I'm going to hit OK, spread out the columns here so I can read things. And here are the results from the F-test. So how to interpret these results, right? So with this F-test, the null hypothesis is that there's no statistically significant differences in the variances, in this case, between our 2 samples, which are class A and class B. So how to know whether we're going to retain or reject that null hypothesis, right? Quick way is that we can look at our p-value. So in this case, we see that we have a very small p-value, 0.0059, right? Well below a alpha level of 0.05. So that's going to indicate to me that we're likely wanting to reject that null hypothesis, instead go with the alternative hypothesis that there is a significant difference in the variances between class A and class B samples. So that tells us that we're going to use the t-test for 2 samples, assuming unequal variances. So a bit of an extra step when using Excel, but once you get onto it, it's not too bad. So now that I've got I know which test I want to use here, I'm going to go back into my data analysis window here. I'm going to select the unequal variances test. And same kind of idea, I'm going to enter my data values for the 2 variables. So class A, enter the values for class B. Notice that I've put the labels in there, so I'm going to click on the labels box. I'm going to keep my alpha value at 0.05, and I'm going to select where I'm going to have the output of the results just below where my F-test results were. Okay, and hit OK. So there are the results for my t-tests for 2 samples, assuming unequal variances. So here's the results right here. So how can I interpret this? Well, we're doing a 2-tail test. We're just wondering if there's any differences or not. So our t critical, that's our critical value for the t-test, is 2.06. So again, it's a 2-tailed test. So we're going to take the positive and negative values of that critical value. So now we can delineate the regions of rejection and non-rejection. So there's our critical values, 2-tailed test, so positive and negative values. So now we're going to calculate the test stat, which Excel already did. Right, so there's our t-stat right there, 2.18. So plus and minus 2.1 gets rounded up to 2.19. So we go back to our diagram, right? Our critical values are there, and our t-stats just land outside of the critical values within the rejection zones. So now we can make a decision regarding the null and alternative hypothesis. So as I imagine you already guessed, we're going to decide to reject the null hypothesis at an alpha level of 0.05. So basically this is telling us that the final grades between class A and class B are significantly different at an alpha level of 0.05. We can also look at the p-value that Excel gives us for the two-tailed test. So 0.04. So again, that tells us that there's about a 4% chance that we're committing a false positive type 1 error. Okay, so on to the third type of sample t-test. So in this one, it's called the paired sample t-test, and it's called pairs because we're looking at individuals, right? We have one group at one time where each individual is measured for something or surveyed for something. And then some time passes and they go back and measure each individual at a later time. And this test is used to see if there's a significant difference in time between the group after relative to the group before. And so you can imagine each of these people, right? Each of these people is a pair. It's the same person. They're measured at one time and then measured at a later time, right? So that's why it's called the pair samples t-test. So we use the paired samples t-test a lot to see if there's any change in a variable over time, right? So time also used a lot in treatments, right? Does a drug have a significant effect on some health condition? And we'll look at an example like that. Growth, right? Things like that. So often we're using the paired sample t-test to see if there's any before and after effect by some treatment. So again, just kind of a summary, we're dealing with two samples. We're dealing with continuous data. In this time, we're looking at pairs, right? These are matched right before and after. So that's unlike the independent samples t-test where there is no pairing before and after. Still parametric. So we look at our table here, right? We're dealing with continuous data. Our two samples, tests that we just did previously. But now, because we're dealing with matched pairs, we're going to be using the paired or dependent sample t-test. Okay, let's do an example. So imagine there's a new drug that comes out, and the drug is intended to improve people's moods. So to test whether this drug improves people's moods or not, 15 patients are asked to rate their mood before and after taking this drug. So we have 15 people. They're asked to rate their overall mood at one time. Then they take a drug, right? That's supposed to or intended to improve their mood, and then they're surveyed after taking the drug to see what their mood is afterwards. So we have two groups here, and this is common in a lot of drug trials, right? We have one group called the treatment group, which are actually giving the drug itself, and then we're giving a control group, where basically they're just given a sugar pill. There's no real drug or medicine within the treatment itself, but the control acts as a comparison. Okay. So this example is also in the Excel workbook called t-test_paired. So here's the data right here. So we have 15 patients. On the left box here, this is our drug treatment, our medication treatment. So this is people's surveyed moods before given the medication, and this is their surveyed moods after given the treatment. And then we have the control group. So the control group thinks that they'll be given some treatment for their mood, but they're actually just given nothing, really, like water or sugar pill, right? They're also, right, surveyed for their mood before the placebo and their mood after the placebo. So this is a way to compare the drug treatment versus the non-drug treatment. So essentially with this scenario, we're doing two paired samples t-tests. We're going to be comparing the moods for people before and after that are actually taking the drug treatment. And we're also going to do a paired sample t-test for the people that are taking just the placebo. Okay, so let's go through our steps in doing our hypothesis testing. So let's state the null and alternative hypothesis. So the null is that there's going to be no difference in mood before or after either the drug or the placebo treatments. If we reject the null hypothesis, we're saying that there is a difference, significant difference, statistically speaking, in the mood before and after people taking the drug or people taking the placebo treatments. So in this case, because we're trying to see whether there's an improvement in the mood of people after taking the drug or the placebo, we're doing a directional test. In this case, we're doing a right-tailed test because we're seeing that if there's a significant increase after the treatment compared to before the treatment. So we're interested in the direction. In this case, we're looking for an increase or an improvement in mood. So we're going to be doing a directional right tail test for both the drug and the placebo groups. Right, so if we're going to define our rejection and non-rejection zones, right, anything that lands in here is our non-rejection. Here's our critical value, right, and then if anything that lands in here, we're going to reject the null hypothesis. So of course, we're going to be using these 7 steps again. And we can also do this calculation in Excel. So in Excel, in the data analysis tab, we have the t-test paired 2 sample for means. So that's a test we're going to use in Excel. Right, so the same kind of procedure. You're going to be inputting your variables, so before and after for both the drug treatment and the control group placebo group. So here's the outputs or the results for both the drug treatment and the placebo treatment right there. So what are the results? Okay, so let's first look at the output table for the drug treatment. So we're doing a one-tailed test. So our critical value right here is 1.76. That's what we're going to be comparing our t-stat to. There's our t-stat, right? It's minus 2.49. We're going to take the positive value of that. And since our t-stat is much greater, right, than our critical value, we're going to reject the null hypothesis that there is no significant difference in mood before and after the drug treatment. And we're going to go with the alternative hypothesis that there is an improvement in mood. So essentially what we have here, our t-stat is well within the critical region, right, well above the critical value. So we're in the zone of rejecting the null hypothesis. So once you've done that, right, as I already said, based on the results, we're going to decide to reject the null hypothesis and say that there is a significant difference in improvement in mood after taking the drug at an alpha level of 0.05. But that's just for the drug group. Let's look at the placebo or control group. The same kind of idea here. Critical value is going to be the same, 1.76 for the placebo group here. Our t-stat is 1.29, so a much lower t-stat for the placebo group. And since the t-stat is less than or less extreme than the critical value, we're going to fail to reject the null hypothesis. So in this case, the placebo t-value lands within the non-rejection zone, while the drug treatment t-value landed within the rejection zone. Right, so basically at the end, our conclusions can be by comparing the results from the drug treatment and the placebo treatment, right? At the 95% level, the drug treatment shows an improvement in mood among the patients, but the placebo treatment at the 95% level does not show any improvement in mood among the patients. So you can also use these online calculators to do these paired t-tests, right? So there's the before drug, there's the after drug. I've entered the data, 2 columns right there. Right, gives me the same t-value, 2.45 essentially. And there's my p-value, 0.028. So a very small p-value, very small chance I'm committing a type 1 false positive error. And so we'll end off here for today with t-stats. So our next lecture will be looking at when we have to compare two or more, I should say more than two samples. So something called ANOVA. So I'll let you guys go for today. And I'll see you next week.